Okay, so if I have tissue, and this tissue is, you see this tissue over here, and these dots, what do these dots represent in my tissue? What do the dots represent? Yes, nucleus, excellent. So we know that dot is a nucleus. Each cell has one nucleus, and multiple cells give us a tissue, and multiple tissues give us an organ, and multiple organs working together give us a organ system. Okay, so this tissue, what is this tissue doing? There's red things and blue things. Obviously, there is a lot of metabolic waste. So metabolic waste is something that's negative. Metabolic waste, such as we mentioned last week, 2,3-BPG, also known as 2,3-bisphosphoglycerate. That's also negative, but there's a lot of it, a lot of this toxic negative 2,3-bisphosphoglycerate, a lot of other metabolic waste like nitrogenous waste, mentioned last week by Abraham. Nitrogenous waste, that's a form of waste. Nitrogenous waste, as well as high amounts of concentration of carbon dioxide. So that looks like a diseased tissue. Okay, what else does it have that's low? It has low oxygen. The tissue has low oxygen. Okay, and the tissue has low oxygen. Why does the tissue have low oxygen? Why does the tissue have low oxygen? Why does the tissue have low oxygen? Why do our cells have low oxygen and they need oxygen to come from the blood? Why is that? Yeah, so they are breathing, they are consuming that oxygen, known as aerobic respiration. So aerobic respiration, consuming oxygen. And also we have, what else do we have? Excellent, oxidative phosphorylation. So these are consuming my oxygen level. That's why I need the blood to come through. Now we're going to talk about another, so all of these are stress. Metabolic waste is a stress. High carbon dioxide is a stress. What else that's high in the blood? What else that is also high in our tissue? In our tissue that's also high. That's hydrogen proton. Hydrogen proton concentration is also high. So you need to know what a bad tissue, nasty tissue look like. These are the features of a suffocating tissue. So it always has low oxygen and low partial pressure of oxygen because oxidative phosphorylation, who's consuming ATP. So we use oxygen to consume ATP. Where in the cell does oxidative phosphorylation happen? Where in the cell? Obviously, is it in the Golgi body? Is it in the nucleus? Is it in the endoplasmic reticulum? Is it on the cell membrane? Where is it happening? Where does oxidative phosphorylation happen? Excellent. So it happens inside the mitochondria. So that's why we said it doesn't make sense for the red blood cells to have a mitochondria inside them. Why not, Nicole?
Because they never consume the oxygen, even though it's supposed to take it.
Excellent. Very good. So, you guys, excellent. You have the idea. But when you use pronouns, it will take the oxygen. So who's it?
The mitochondria. That's why red blood cells, they're anaerobic.
Yes, so the red blood cells, they are anaerobic, excellent, because if they were aerobic, they would need a mitochondria, and the mitochondria would consume the oxygen. Good. So now you know what a nasty tissue looks like. Has high acidity, high carbon dioxide, high 2,3-bisphosphoglycerate, high nitrogenous waste. So I need my oxygen to come there to fulfill that. We've dealt with that with our cardiovascular system. Now we're going to look at another nasty or dangerous thing, and that is infectious microbes. These infectious microbes are like bacteria, parasites, fungi, bacteria, parasites, fungi, and viruses. So they need to be destroyed. And who destroys them? We talked about that. We said that your white blood cells, if this is a microbe, a virus, bacteria, a parasite, what happens is we have phagocytes. What is phagocytosis? Phagocyte means swallow. Phagocytosis means swallowing or engulfing. And the cells, the white blood cells, are known as phagocytes. So they swallow. So what happens is they come close to the bacteria. Then they have pseudopods. They crawl. We talked about that. And they crawl, and once they crawl, they surround our microbes like that. Then when they surround the microbes, what's going to happen next? They will, this is the bacteria, the virus, the parasite, they will engulf them. Then they will close them inside in a vesicle, in an intracellular vesicle. Bacteria, virus, parasite, in an intracellular vesicle. This intracellular vesicle, what's the fate of it now? So now that's a white blood cell. This one is a white blood cell, and this is our vesicle. This is our phagocytic vesicle. We use phagocytosis. That's our phagocytic vesicle. So now this phagocytic vesicle is inside. You have two balloons inside. So what's going to happen now? What's going to happen is you're going to have, remember we said they have granules. These white blood cells, they have granules. And the granules, what do they have? They have enzymes. They have proteolytic enzymes. They have metalloproteinases. They have degradative enzymes. They have ROS. What's ROS?
Reactive oxygen species.
Excellent. They have reactive oxidative species. So all of these represent what? Weapon. These are weapons. So now you're going to have a fusion where these are called lysosomal vesicle. And this is phagocytic vesicle, two vesicles. But now what will happen is they will fuse together. Like that. So now you will have all of these knives, these dangerous weapons. What are they going to do? What are they going to do to the bacteria and all the stuff that's inside? They're going to break it down. And when they break it down, then your white blood cell is going to excrete them out like little blebs that are harmless, digested blebs, harmless blebs, because now they are destroyed. They have inside this destruction. So this is known as the phagolysosome, because they merge together, they fuse together, known as fusion. This is the fusion of the phagolysosome. Now, in order for this to happen, your immune system must have a way. Your immune system must have a way of getting to the right destination. So this tissue that I have, this tissue that is now, so we have different types of stress that the cell can undergo. When you have too much carbon dioxide, when you have too little oxygen, when you have too much acidity, when you have high temperature, these are all different kinds of stress. High reactive oxidative species, like drinking too much alcohol. So now the reactive oxidative species that's supposed to be used to destroy the microbe is going to be destroying your own liver and causing alcoholic liver disease. But now we're talking about a different stress, and that is infectious diseases, infectious organisms. So the tissue is a large compartment. The tissue compartment is a very large compartment. The tissue compartment is a very large compartment. And how do we know? So now the blood vessel, we agreed last week that the blood vessel is a really long, that they are made up of cells. And the blood vessels have 3 layers. What is the outermost layer called? What is the outermost layer of the blood vessel called? Excellent. Tunica maxima or tunica externa. Tunica maxima, tunica externa, and it is also known as the tunica adventitia. So these are all on the outside. On the innermost, where you have these dotted endothelial cells, these endothelial cells represent for me my inner layer, my endothelium. My endothelium represent for me my endothelium. So now let's say the tissue is all around. The tissue is all around. The tissue is all around the blood vessel. The tissue is all around the blood vessel. The tissue is all around the blood vessel. So now let's say this region right here is damaged. There is damage in this region. There is destruction in this region. There is a virus in this region. There is bacteria in this region. This is a problem. Virus, bacteria, this is a problem. This problem now, how can it be repaired? What happens is you have your monocytes. Your monocytes. These are a primordial form of the white blood cells, known as macrophage, but they are not in the form of macrophage. They are form of a monocyte. Later on, why do they stop here where there is infection? When there is infection, people mix up infection and inflammation. They're not the same. Inflammation can be caused by infection. Inflammation can be caused by infection. But so every infection is an inflammation, but not every inflammation is an infection. Reactive oxidative species lead to inflammation. Drop in carbon dioxide, drop in oxygen saturation leads to inflammation. So what is inflammation? Inflammation is the immune system protective response to bring more blood to the tissue who is damaged, to supply the tissue with oxygen, to supply the tissue with nutrients for ATP, carbohydrates that we can break down through glycolysis and get ATP. Lipids, we break down through beta oxidation, get ATP. In addition to proteins, through protein catabolism, break it down and get exergonic energy through endothermic reactions. Through hydrolysis, we break them down and we catabolize them. We break these covalent bonds and we get energy. And nucleic acids carrying ATPs, okay? So ATP, GMP, CMP, these are all energy carrying molecules. So we need to supply the blood with all of that. we need to supply the tissue with all of that. So now I have an infectious problem. How does my monocyte recognize that the infection is here? Why doesn't it go to this one, or this one, or this one, or this one, or the others? Why does it have to stop here exactly? Yes?
It has different proteins.
It has different proteins.
So let's say if it's a virus or a bacteria, they'll have a different protein that's not associated with the rest of your DNA.
Excellent. So you are in the right direction. So you know we said that in crime scene investigation, you have your own fingerprint, you have your hair falling off when you walk into the crime scene, and you have like some tissues falling off that has your DNA. But what happens is for bacteria, viruses, on their surface, they don't have a fingerprint. What do they have? They have something called the glycocalyx. The glycocalyx. The glycocalyx is a nice word for two things. Glycoproteins and glycolipids. So you know on the plasma membrane you have lipid and you have some sugars attached with these lipids. You have some sugars attached with these lipids, and you have sugars attached with these lipids, and you have proteins like receptors on the surface, and we have protein channels on the surface, and all of them have proteins that have sugars attached to them. So these are sugars on the surface who are attached to lipid, and sugars are on the surface who are attached to protein. But we don't say twice. We don't say sugars with protein, we say glycocalyx. Glycocalyx is the overall unique set of sugars and proteins on the surface of your cells and the cells of all the microorganisms. If you are alive, you are made up of cells, and your cells have cell membranes. On the cell membrane, this is on the membrane, on the surface, you have sugars attached to lipid, sugars attached to protein, and that's different between everybody. The only ones who have the same glycocalyx are the identical twins. But everybody else has your own glycocalyx. So now your immune system uses that glycocalyx to recognize and identify self from non-self, to be able to identify self from non-self. So now the immune cells are screening the tissue. That's glycocalyx. That's me. Sugars and proteins, sugars and lipids, that's me. Sugars and lipids, that's me. Sugars and lipids, that's me. Sugars, what is that? That's not me. That is, for example, that is bacteria. That is virus. So, and also there is debris that falls off. Debris that falls off from the side of the damage of the infection. You know, this infectious organism, this bacteria, this virus, this parasite, bacteria, virus, parasites, fungi, they're not there living inside the cell and the door is locked. They are in there destroying the tissue. So when the tissue is destroyed and damaged, things are sprinkle. Things are falling apart inside the environment. So all of those powder, all of that debris, that necrotic powder, what's going to happen to it? It's going to be detected by the monocytes. It's going to be detected by the white blood cells. And then the white blood cells are going to say, oh, here it's fine. It's like when the police are patrolling and they hear somebody screaming, help, help. Why don't they go to the other house? Or the one that's before. Why this one? It's because they heard the sound come from here. But these monocytes don't have ears. They have receptors. And the receptors bind that necrotic debris, and they are able, sometimes they even internalize it, bring it in, analyze it inside, and say, oh, that does not look like our cells. That looks like bacteria cell. And that's how they find out. And then they go and damage that tissue. And then they go and they remove the damaged tissue, and they do the phagolysosome. They do, and they engulf and swallow not just the microbe, but even the dead tissue. They remove all of it. They carve it out. Remove it. Make a whole clean space. Then your body will do healing. And when your body heals, then a new cell is going to be built, and that is known as healing. Healing by first intention, or healing by regeneration. If the tissue can regenerate, it will heal. But some tissue is locked in a state of quiescence. It does not divide. So then, if it cannot divide, what happens? We have it empty. You just leave it empty like that? No, we dump cement on it. But that cement is not actually cement, it's fiber. So we dump fiber tissue. We dump fiber tissue here. Okay, so that's not a cell anymore, that's fibrous tissue. That's called healing by fibrosis. But what you need to understand is that this infectious stress is tracked down by your immune system. And your immune system relies on your cardiovascular system to pump it to the right place. That's why the police, there's a separate police department, but they use the MTA to get to the side of the traffic, right? They drive a car. A car is not a police, a car is a different system, transportation system, but they use it. Same thing, the immune system relies on the heart and the blood vessels to pump it to the right direction. How does the immune system get out to the site where there is an infection? How does it get out to the site where there is an infection? How does it get out? How does it get out here? It's going to remain in there? How does it make its way out here? I mentioned that last week. How does it get out to this place? Remember we said these cells, they're going to retract. They're going to pull upward. They're going to pull upward like that. And they're going to pull back. They're going to pull back like this to open a gap, to open a passageway, to open a gap so they can get out and fight for us. This gap, what is that gap called? It's called an inter. It's between two endothelial cells, so it's endothelial gap, and some other books call it endothelial cleft. Interendothelial gap and interendothelial cleft. Are we clear? Okay, they get out and then they do the phagolysosome reaction and they engulf and internalize all the necrotic and dangerous debris, destroying it and then expelling it out as edible, harmless, digested blips. Okay? So now you understand how we rely on a system that detects with receptors. What is this process called? I mentioned it last week. When you use chemicals to start heading to the site of where the problem is, like how you smell something delicious and you walk toward the kitchen following the sound, following your sense of smell, your olfaction. What is olfaction? The sense of smell. You guys never heard of that word before. Olfaction. You heard? You did not hear it. Raise your hand if you did not hear olfaction before. You guys are aware of it. It was part of last semester's work. So you rely on olfaction. That's olfaction taxis. But here, when we rely on chemical, that is known as when you rely on, that's chemotaxis. That is chemotaxis. So we chemotax, we crawl. We crawl using what? This cell is going to crawl using external, is going to use external processes known as, we mentioned them last week, pseudopods. Remember the pseudopods? They are used for crawling and chemotaxis, and you have cytoskeletal proteins that push the cell to head to the site of the damage. Okay, and this is very important because we also have to recognize that some cells are specialized to destroy a particular set or a particular type of infectious organisms, such as as neutrophils. Neutrophils are specialized for bacteria. Neutrophils are specialized to detect bacteria. Then you have eosinophils and basophils. Basophils stain basic. That's why they call them basophils. And they attack parasites, and they attack also different forms of parasites and fungi. Eosinophils target some forms of bacteria, viruses, and parasites. So we have to be very concerned. And when white blood cells, when you have too little white blood cells, when you have a deficiency in making the white blood cells, how does that affect your immune system? So it causes hypo or hypo immunity. So now we are going to, this is what happens in HIV. Because in HIV, your body is making white blood cells. But what is the problem? The white blood cells are targeted by the HIV virus. So the HIV virus does not target your nose, your eyes, does not target your heart, does not target the tissue. It targets the white blood cells. So now it stops the activity of white blood cells. So now imagine the police department goes on a strike. No cop in the world. No cops. No cops. We're just living like this and there's no police officer. What's gonna happen? The criminals are gonna increase in number and they're gonna destroy the city. Not that the cops are doing excellent and they stop the crime and everything, but it's gonna become even worse. So the same thing here. These are our cops. These are our police officers. They are destroying all the bacteria who harm us. Okay? Yeah, I call the cops sometimes, they don't help you. Raise your hand if you called the cops within the last week. Raise your hand if you called the cops within the last 2 weeks. Wow. So we are one group now. Raise your hand if you called the cops within the last 3 weeks. Last 4 weeks. Last month. Wow. Last 2 months. Last 3 months. Last 4 months. Last 5 months. You guys live in heaven? Last 6 months. 7 months. 8 months. 9 months. 10 months. 11 months. A year. Wow. You have an anniversary of not calling the cops. Do you live in 7th heaven? Yeah. I called the cops 2 weeks ago. For what?
Did they help you?
No. Did somebody say for what? Did somebody say for what or no? Yeah. The guy was selling, he lied to me. He was selling rotten, molded bagels. So I looked at them, and if it looks like a cat, walks like a cat, it's a cat. No, I'm just saying that the sandwich, the bagel cream cheese looked bad. But I looked at it, and it was a smoke shop. And then I looked and I said, when were they made? He said they were made this morning, sir. He knew why I was asking. So I said, okay. I bought them. I took them. I was lecturing. I took one bite. It tastes like sponge. So I just spit it out, and I looked and I see green dots. I said, okay, I cannot wait for the lecture to be over. And then they said, no, that's Department of Health. We can do nothing for you. Blah blah blah. Anyways, but these guys, they will always help you. These white blood cells, they are there for your support.
Unless they're returned.
Yeah, but then they are not working. Them is not like they are working, but they cannot help. But them, they are themselves sick. He is inside them. The HIV is inside your white blood cell. He couldn't find nobody else to infect. The HIV could not find anybody else to destroy but your white blood cell. That's what it completely eliminates, completely obliterates your immune system. Okay? Alrighty. Then you have to understand this process is very important, how we are doing immunosurveillance. And then there is hyperimmunity. Sometimes, like your immunity is too weak, and that's called immunosuppression. Sometimes Your immune system, this word is very important, immunosuppression. Immunosuppression. So the HIV patient are immunosuppressed. Sometimes a genetic problem causes your glycocalyx to look a little different than it's supposed to. So your immune system is going to assume that it's bacteria. So that's what happened with autoimmune arthritis. Whenever you hear autoimmune, what should you associate it with? It's another word that starts with A. Autoimmune disease is the same thing as autoimmune disease is the same thing as amnesia. Amnesia, A for A, is amnesia. Autoimmune system is amnesia of the immune system. So the immune system now is unable, the immune system is now unable to remember who's self from non-self. What is immunosurveillance? It's when you're patrolling, when the immune cells are patrolling, looking for chemotaxis. There's something I can detect. Something I can detect. That's immunosurveillance. That's immunosurveillance. And you need to know autoimmunity. So autoimmunity is when your own immune system destroying the ligaments of the cartilage of your bone. What about, we have another example. What about in diabetes, type 1, juvenile diabetes? What happened in juvenile diabetes? Yes, what happened in juvenile diabetes? In juvenile diabetes, your immune system, in juvenile diabetes, your immune system is going to send antibodies to destroy your own pancreas. So now your own pancreas is destroyed by the antibodies of your own immune system due to a genetic defect. So we know that what does the immune system relies on to destroy infectious organism? What does it rely on? So white blood cells, that's very good. So now you're talking about innate immunity. So these guys represent for us these white blood cells who will go and fight, and you call them, that's part of your innate immunity. So the first part of your innate immunity is your skin. That's a fence. You know now Trump want to build the border because he thinks the people coming from outside are bacteria, so he want to build the border. So the same thing, your body has border to protect you from enemy. You know, they say if you live in a country that has a lot of mountain, you're lucky, your enemy cannot get through. You know, they need an elephant. They need to ride an elephant so the elephant can help them go. Even the car cannot get up the mountain. The elephant can do it. You know elephants climb the mountains. But anyways, these are form of mechanical innate immunity. That is what you rely on naturally. Innate immunity, natural immunity. Okay? Another form is these neutrophils, these white blood cells. These are a type of innate immunity. Then when the problem lingers on, so this, don't think that these white blood cells, don't think that these neutrophils, these eosinophils, these basophils can win all the time. Sometimes the virus or the bacteria or the infectious microbe, so the bacteria send a lot of toxins, endotoxin, exotoxin that destroy the tissue. Sometimes the bacteria is too strong, so we need to move to phase 2. So phase 1 is known as innate immunity. That's the innate meaning natural. And it is non-specific, destroys everybody holistically. Like the cops, any problem that happens, there's a fight, there's some problem, they will come for that. But then if it gets really serious, then the detective will come in. And the detectives are specialized. There is a detectives for homicide, detectives for fraud, check fraud, detectives for robbery. They are different. So when the problem now gets beyond, far beyond innate immunity, now you need adaptive immunity. And that is more specific. And in adaptive immunity, we need B cells and T cells. So B cells are called B cells because they mature in the bone marrow, and T cells are known as T cells because they mature in the thymus. Okay, so that is a form of specific immunity. Any questions so far? Yes.
Okay, so you said when you have a weak immune system, what is it called?
Immunosuppression. It's immunosuppressed.
And then, when you were mentioning the macrophages have pseudopods, or crawl?
Yeah. Crawling is the action. But who enables that to happen? Flying with an airplane. So the airplane enabled you to fly. So the pseudopods enable the cell to crawl. So they start crawling based on chemo.
So they have pseudopods, or pseudopods is the action?
No, they have pseudopods are the vehicle. These are cytoskeletal proteins like cilia, flagella, okay? The microfilaments of the microvilli. These are your extensions of the cell membrane. They are on the cell membrane, they extend. They are extensions of your cell membrane. Okay, then we have to understand, we have to now go back that immune system, we have to go back that the immune system is responsible for our defense. Immune system is responsible for our defense and is divided into innate or natural immunity. It is also divided into adaptive immunity. The innate immunity is like your skin. Your skin is a barrier, is an epithelial tissue barrier. Your skin. What else did we say? Your granulocytes. Why do we call them granulocytes? Yeah, they have granules. What are the granules full of? What are these granules inside the granulocytes full of? They are full of? No, the neutrophils are granules. But what are the granules are like bag. Granule is a bag. The bag is full of what? The bag that fused with our dangerous infectious microbe. What is it called? What is it called? The granules that are inside. We said there is enzymes, lysosomal enzymes, degradative enzymes, proteolytic enzymes. We said metalloproteinases, reactive oxidative species, acid, hydrogen, proton. That stuff is dangerous. So what is inside the granule, guys? The white blood cells have granules inside them. These are known as your neutrophils, your eosinophils, and your basophils. neutrophils, eosinophils, and basophils. They all have granules inside them. They all have granules inside them. They all have granules inside them, but they don't look the same. But these granules, what do they have inside the granules? They have acid, hydrogen proton. They have metalloproteinases. Okay, acid metalloproteinases. What else do they have? They also have proteases. They also, in addition to proteases, what do they have? Degradative enzymes. Lysosomal enzymes. We can go on and on forever. Reactive oxidative species. Reactive oxidative species. ROS. All these things are weapons. These are weapons that help the granulocyte destroy all the invading microbes. Okay. Then we also have natural killer cells, NKS. These are natural killer cells. If things get really worse, then we move on to phase 2. If things get really worse, we move on to phase 2. If things get really worse, we move on to phase 2. And phase 2 will be adaptive immunity. And in adaptive immunity, we have two kinds of cells. B cells, and they are called B cells because they mature in the bone. They mature in the bone tissue. While T cells mature in the thymus. So the thymus is in your mediastinum. Is where when you wear a necklace is different. The thymus is different from the thyroid gland. Thyroid gland is right here in a thyroid. The thymus is in your mediastinum. So this thymus is where the T cells mature. But the thymus has a problem. The thymus undergoes natural involution. Involution. The thymus has involution. What does involution mean? It means deterioration. So the thymus was this big, it deteriorates into this big. It gets really small. And the more it gets smaller and gets smaller and gets really small, so that means we will not have the capacity to mature a lot of T cells. So that means our immunity will go. It will decrease. So when does involution happen? With age. So the older you get, the smaller it's gonna drop. So that's why the elderly people have a very weak immune system, because the T cells are not working. So the B cells, this is called B cell mediated immunity. B cell mediated immunity, and this is known as T cell mediated immunity. And what happens is T cells go and attack tissue them. They have more weapons than this. I mean, obviously this did not work. The acid and the metalloproteinases and the proteases and degradative enzymes, proteolytic enzymes, lysosomal enzymes, reactive oxidative species, that stuff did not work. That's why we move into phase 2. So now you gotta know how they work. The T cells, they will go there. They have big weapons. I mean, this is the taser and all that. That doesn't work. Then they have the big rifle. They have like really more extensive, more dangerous machinery to destroy the tissue. So the T cell itself it fights and destroys dangerous, infectious organisms and dead tissue. But the B cell is different. The B cell, it will not itself go and fight and destroy and damage. It will not do that. It will send, it is like a helicopter or like Air Force. In the Air Force, the airplane itself is not going to go in there fighting. It's going to throw missiles from far away. It's going to throw bombs from far away. So same thing here. Same thing here. The B cells are going to throw away these are the missiles, these are the bombs, antibodies. So the antibodies are going to go and destroy the tissue. Okay?
Is that why this one gets destroyed easily?
I'm sorry?
Is that why the T cells get destroyed easily? Because it fights by itself?
Yeah, it fights by itself. It has all the weapons. What do you mean? Like it get destroyed easily?
No, it said
Involution. So involution, that's not what happened to the T cell. Involution is what happens to the thymus. So the thymus is a gland. Excellent question. The thymus is a gland. The gland is the site where the T cells mature. So the T cell goes, so all the blood cells come from where? Where do all the blood cells come from? Thank you, the bone marrow. And they go from the bone marrow to mature in the bone if they are bone cells. They come from the bone marrow. If they go from the bone marrow to the B cells, they mature. They will mature in the bone. But if they go from the bone marrow to the thymus, then they will become T cells. And the thymus, and by the way, it's two different types of cells. So it's not like the same cell is going to go here become B cell or there become, no. If you are a primordial B cell that will mature. Remember, you mature there. You're not born there. You mature there. So you already are made in your bone marrow, but you mature there. And the T cells, they are made in your bone marrow, but they mature at the thymus. Very good. Okay. So you have to know that one matures in the thymus, one matures in the bone marrow, one fights itself. It goes in combat like the SWAT team. Yes?
If the elderly experience of immune deficiency because of involution, why do
Because involution of the...
right,
Yeah, let's talk like that. Complete sentence. Yeah, excellent.
then why are children also especially susceptible?
Because children are the opposite. Their thymus is still beginning to mature. So when you are born with a tiny thymus, and it gets bigger and bigger and bigger. When you get into adulthood, it's big. Then when you get into late adulthood, it's going to start to involute. Okay? Alrighty. So remember what I told you. If you want to know the difference between two things, recognize the similarities first. What's the difference between the B cells and the T cells? The B cells and the T cells both are specific. They are not generalized immunity. These are specific immunity. So they are very specific. And the B cells, they rely on memory cells. They rely on memory cells. So when an infection happens, they're gonna rely on memory cells that stay there, and that's how vaccination and immunization happens. You have a weakly attenuated form of your pathogen, your microbe, this infectious microbe. It's gonna be an infectious microbe that is weak or destroyed or homogenized, blended. But the glycocalyx still there, the surface proteins are still there. So your body, remember how your immune system works. Your immune system works by recognizing the surface. Your immune system works by recognizing the surface of your microbes. So now even if you give it dead microbes, it doesn't matter because the surface, even if you're dead, your surface proteins are the same. So you give it a vaccination and then your immune system is going to say, it's going to get used to it. So next time, now there's memory cells going to remember it because it was exposed to it. So next time when you get an infection, next time, then your body has already developed the memory cells to go and to initiate mature cells who are B cells to go and destroy that site, that infectious organism. For T cells do not rely on antibodies. They rely on cytotoxicity. So these are known as cytotoxic T cells. So we have two different types of T cells. We have cytotoxic T cells and we have helper T cells. Cytotoxic T cells, we have two types of cells, one known as cytotoxic T cell and the other is known as helper T cell. Cytotoxic T cells and helper T cells. Cytotoxic T cells and helper T cells. Okay, so we have helper T cells and we have cytotoxic T cells. These are the two different types of T cells. The helper T cells help cytotoxic T cells kill the infectious organism or the infectious microbe. Then you also have to know when you have autoimmune disease, when your own immune system is destroying your pancreas, like in juvenile diabetes, when your immune system lost memory, when your immune system has amnesia, who is your immune system using to destroy your own pancreas? Like in lupus, your own immune system is destroying your body, your nervous system. Who is your immune system using to do that? It's those T cells. Okay? Those T cells, the T cells are the ones who are implicated in the destruction of your tissue. Okay? Any questions? Infectious organisms, microbes. So these are key concepts that we're going to discuss and we're going to see it in the slide some more, and we're going to see it on the slide. And then now we got to go into the lymphatic system. We got to go into the lymphatic system. We did immune system. We got to now look more into the lymphatic system. The lymphatic system is a support system. It's always in green. So we know that the heart pumps blood. The heart pumps blood, and the blood goes out to the tissue, and we say we have two halves of a circulation. We say we have two halves. One half that is red. One half that is red in the cat. And what is this compartment called? The compartment with holes where things are exiting for the tissue. So that is my tissue. I'm sorry? Excellent. That's the capillary. The capillaries. So we say we have a red half and we also have a blue half. And everything returns back to the heart. And we said that on the red half, good things are coming out. So who's coming out to the tissue? Oxygen, oxygen, plus oxygen. That's good. We need that. Oxygen and nutrients for ATP. Who are my nutrients for ATP? Carbs, carbohydrates are broken down, proteins, lipids, okay, as well as hormones, everything that your body needs. And how does it come out in this direction? What causes it to come out? Because we said we don't have movement for no reason. Kinetic energy, very good. And who's causing the kinetic energy? Who's causing it? I'm sorry? Yeah. So the heart is pumping and the blood is coming out like here and then rushing out like toothpaste, filtering out. That's filtration. This process right here is known as filtration. That's known as filtration. Are we clear? So, who's powering filtration? The heart. What kind of pressure is that? What kind of pressure powers filtration? Excellent. Very good. Very good. Very good, Nicole. That is hydrostatic pressure. Hydrostatic pressure from the heart. So the heart is applying hydrostatic pressure, and hydrostatic pressure is causing the filtration of substance to come out. Okay? Then we have good things that came out, and we have bad things that are gonna flow in. So here the direction is to flow inwardly, 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 inwardly. And that would be the metabolic waste, carbon dioxide, metabolic waste such as 2,3-bis-phosphoglycerate, in addition to 2,3-bis-phosphoglycerate, in addition to carbon dioxide, in addition to 2,3-bis-phosphoglycerate, carbon dioxide, and in addition to what else? Acid, hydrogen proton concentration. So all of the bad things are flushed backward. But there is a big problem. There is a big problem. And that's where we need our lymphatic system. The big problem is that coming out, 100% comes out. But getting back in, because here we rely on hydrostatic pressure. But here, what do we rely on? What do we rely on? Sucking things back. The bad things entering into the venous side, the blue side. What is that? What powers that movement? It's not ATP. Yes?
Kinetic?
It's kinetic, but why kinetic in that direction? Why not kinetic from here to there? Yes, Tony, what is it? Osmosis. Perfect. So that is the osmotic pressure. So here solutes are going to be moving in here through osmotic pressure. Through the osmotic pressure. Fulfilling it, there is an osmotic gradient. Osmotic gradient. Osmotic gradient. Okay? But the problem is only about 80% gets back. Only about 80% get back. And 20% lags behind. 20% lags behind. So what are we going to do now? Leave the 20% there? That's why you have your green lymphatic system, and your green lymphatic system is going to go adjacent with your veins, and is going to bring all the leftover stuff, all the leftover carbon dioxide that could not flow back, all the leftover metabolic waste, all the material, the solutes that left behind, metabolic waste, and all of that stuff flows back parallel. And now it is able, it's like the sewage system. It is able to return all of that to the venous side, so that is now pumped into your lungs. Are we clear what the lymphatic system does? So we have two lymphatic ducts. We have the thoracic duct, and this thoracic duct is very important because it drains an extreme amount of all of the leftover stuff that remains behind. So now there is diseases where there is an obstruction. There is an obstruction of the lymphatic duct. There is an obstruction of the lymphatic duct. What does that mean when you obstruct the lymphatic duct? When the lymphatic duct is obstructed, what does that mean?
It's blocked.
It's blocked. So when it's blocked, what is that going to lead to? Yes? Blood clots, that's in the blood system. This is now, the obstruction is going to cause a buildup, a congestion. A congestion and a buildup of lymphatic material, and that lymphatic material is going to reflux back here into the tissue, and you're going to have extra solute piling up, metabolic waste piling up. So what is that going to affect now? It's going to affect the osmotic pressure. So now instead of all the nasty stuff flowing back to be flushed, now it's going to go from an area, because here there was a lot of solutes here, less solutes here, and the solutes move down concentration gradient and the water follows them. But now due to this congestion, due to this engorgement, what happens now?
Edema.
Excellent, edema. All this stuff lags behind, so now the solutes are going to be moving out to here, and there's a congestion, and water is going to follow, and you're going to have a lot of congestion, and like Ya said, it will have a lot of edema, engorgement. Okay? So that's the key point, and we're going to learn more when we see the slides. We're going to learn a lot more about the lymphatic system. But now we're going to move into your respiratory system. Respiratory system is very important because it is the reason how we're going to flush and remove, how we are going to flush and how we are going to remove, flushing and removing all the metabolic waste. Okay, so when we look at our respiratory system is divided into, so we are looking at anatomy, and physiology. So if we want to discuss or study our respiratory system, we have to look at it anatomically and we have to look at it also physiologically. Anatomically, the respiratory system is made up of an upper respiratory tract. Upper respiratory tract and a lower respiratory tract. Lower respiratory tract. The upper respiratory tract extends from your, so this is the head, say these are the eyes, that's the nose. Extends from the oral cavity, the inlet, and the nasal cavity, the inlet of oxygen, and also the site where carbon dioxide get out through your mouth and through your nose. So it begins from here, then it goes through the nasal cavity and the oral cavity, then you go through your trachea, okay, and then from the trachea you're going into your lungs, and the lungs are divided into different lobes, and the lungs have different bronchioles, primary bronchioles, secondary bronchioles, tertiary bronchioles, and that lastly you have your alveoli. The last part is the alveoli. And then you have the diaphragm here. So your upper respiratory tract, that's when they say you have an upper respiratory tract infection. What happens when you have an upper respiratory tract infection? You have an infection from here up to your trachea. That is the upper respiratory tract.
Sir, please, that one, the second one, what's the name of it?
The second one, where?
The-
Here? Here?
No,
Trachea.
the nose,
The nose?
then to.
Then the trachea.
No.
Trachea. The trachea. Okay? And then we're going to go into the bronchioles. Primary bronchioles, secondary bronchioles, and tertiary bronchioles. Okay. Then, in the end, you would have your alveoli. These are the most important. Alveoli. These are the most important units of your respiratory system. You can have a damaged trachea, damaged bronchioles. That's bad, but it's going to be repaired. But it is your alveoli who are responsible for the exchange of oxygen and carbon dioxide. So what happens here? What happens here is you're going to have oxygen. So the blood circulation is going to come near the lung. The blood circulation is going to come near the lung. And they will be exchanged. Carbon dioxide will go out and oxygen will get in. And oxygen will be bounded by hemoglobin and it will return back into your tissue. It will return back into your tissue. So this is the upper respiratory tract. The lower respiratory tract is from the trachea and below, including your bronchioles, primary bronchioles, secondary bronchioles, tertiary bronchioles, and your alveoli. And what happens here, and so that is anatomically. Physiologically, you have two classifications, and that is conductive respiratory tract, and you have respiratory tract. So meaning anatomically, structurally, you're either part of the upper respiratory tract or you're part of the lower respiratory tract. But when we talk about functionally, physiologically, what does that mean? Physiologically and functionally, you're either part of the conductive respiratory tract. What does that mean? Conductive means you just pass. You conduct. You pass oxygen. That's all you gotta do. Passing things. Like in the MTA, they're just passing you. They don't care where you're going or what do you do. But everything, that's very interesting. Every part of your respiratory tract is part of the conductive respiratory system, except one part known as the alveoli. These represent the respiratory zone of your respiratory system. So everything is conductive zone. This is the conductive zone. It's very important for you to know that everything in your respiratory system is just passing air to your conductive zone, your alveoli. So we're just getting air into the alveoli. You also have to know that your respiratory system is rich in cilia. These cilia have a lot of microtubules. And the microtubules enable the cilia, which are extensions of the cell membrane. And these cilia are able to, they have stroke. They have a power stroke like tails. They are like tails. They have a power stroke and a recovery stroke. They have a power stroke to shove and flush mucus down. They shove the mucus down. And that is very important thing because we don't want mucus to build up in our lungs. And then we get all the air into the respiratory tract, and there the alveoli would come in. The alveoli are going to come in and they're going to exchange. They're going to exchange oxygen. They're going to exchange oxygen with carbon dioxide. So patients who have lung fibrosis, do they have a problem in the conductive zone or do they have a problem in the respiratory zone? When it comes to lung fibrosis. So in lung fibrosis, the tissue, the parenchyma of the lung is unable to fulfill this exchange. This exchange is known as perfusion. Perfusion.
Wouldn't it be in both?
In both where?
If they're fibrosis, wouldn't it be a problem in both?
Yes, exactly. That's what happens. In both what? Conduction?
Alveoli and in the conductive?
No, the conductive is trying to get air to the alveoli. So it's only in the alveoli. So it is only the alveoli who are damaged. So now you need lung transplant.
Because when they have the fibrosis, isn't it hard for them to just breathe in general?
Yeah, so it's hard for them to breathe. Why? Because we are now receiving oxygen. We have no problem conducting it and transporting it and delivering it to the alveoli. It is the alveoli who are damaged beyond salvage. They are damaged beyond repair. They have fibrosis. Remember earlier when I drew that we deposit cement on tissue that cannot regenerate. So now you, because of the smoke, because of all of that, you're gonna deposit a lot of fiber tissue, and then that fiber tissue is gonna dampen all of these cells and they cannot operate.
So the oxygen arrived, they just can't do anything.
Exactly.
Oh, okay.
So now your bone marrow has no way of knowing that. Your bone marrow will say, the integrator in homeostasis will say, oxygen level drop down, let me send EPO. Remember EPO? Erythropoietin. EPO is now going to go from the kidney into the bone marrow to cause the genesis and the extra making of more red blood cells. So now these patients have a lot of red blood cells. Their bone marrow doesn't know that it's not that we don't have enough red blood cells. It's not that we live in a mountain and there is a little bit of air. If you make more red blood cells, you'll be able to trap more air. The air is there, the oxygen is there, we just cannot get it. So now the problem is there is compensatory erythropoiesis. There is compensatory genesis of red blood cells. And how does that affect the viscosity of the blood? It's going to become really concentrated and really thick, and that's going to become hypercoagulable. So the blood is going to be moving really slowly. It's going to become so thick. The blood is going to become so thick like jello, like jelly. And then your heart pressure of the patient is going to go up to push more, push. And then after push some more, they're going to have problems with the heart muscle. And then the blood is going to flow out. The blood is going to exit the blood vessels. And it's not going to be saturated with oxygen. They're going to have blood clots. So the blood is going to clot and clog the passageways, and not enough blood is going to be able to be passed and delivered to the rest of your tissue. Are we clear? Okay, so this is our respiratory system. There's an upper respiratory system and a lower respiratory system. If we're talking about anatomy, if we're talking about structurally. But physiologically, we don't say upper and lower. We say conductive, because now that's the function. Here, the structure is like the structure of the building. You're either on the top floor or the bottom floor. But then you look at the function. Bottom floor is HR. Top floor is blah, blah, blah. You understand? So you have to look at everything in two different systems, structurally and functionally. We looked at the cardiovascular system structurally. It's made up of a heart pump, and it is also made up of blood vessel tubules, and it is made up of blood. Then we studied it functionally. What does it do? Hydrostatic pressure pump. And the blood is flowing. And what are the structures of the blood? Red blood cells, white blood cells. What is the function? One is to deliver oxygen, hemoglobin. The other one is to fight infectious diseases, remove necrotic debris. So we study structure first, always, then the function. Any questions? Does anybody have any question? Please do me a favor, take out a piece of paper and write your